to the frequently asked questions for pre-calculus, and this will be for section 6.1, day 2. Got a kind of a group of word problems here that seem to be keeping everybody from being able to finish this. So, navigation. An airplane is flying on a bearing of 170 degrees at 460 miles per hour. Find the component form of the velocity of an airplane. So, this is bearing. Bearing is not what we use when we are doing our trig. So the first thing we need to figure out is what we should be using in terms of an angle for that bearing of 170 degrees. So you'd go 90 degrees from due north, and then you'd realize, wait a minute, I have to go another 80. So 80 degrees. Now, what angle would that be formed with the positive x-axis? Because this is where we do our trig. We do our trig from that positive x-axis, and that's going to be a negative 80 degree angle. So what we have to do for the component form of this is remember that whatever we have for magnitude times the cosine gives us the horizontal component. So this is going to be 460 cosine of negative 80 degrees, and that will give us our horizontal component. And then no shocker then that for our vertical component we use sine. So if we punch that little bugger in, we'll get what we need. Let me put my degrees in here so that things will make sense. All right, so you punch in 460 cosine of a negative 80 degrees and you get 79.878. And you punch in 460 sine of negative 80 degrees and you get negative 453.012. And that's what they wanted. That's the component form of the velocity of the airplane. So this is all about finding that magnitude. And for the x-coordinate, for the horizontal component, you're going to multiply that times the cosine of whatever the angle. That angle, of course, needs to be relevant to the trig that we're doing, which means with the positive x-axis, what was that angle that was formed? So 43, similar, but now we've got a couple of things going on here. We've got an airplane that's flying on a compass heading, a bearing of 340 degrees. So almost all the way around. In fact, we're just 20 degrees short of it there. And that's going 325 miles per hour. That's not going to be readable up there. Here, we'll do that. And we've got a wind blowing with a bearing of 320 degrees. And that other one was 340, so we just want to go about 20 short of that one, because that is 40 miles per hour. And A says find the component form of the velocity of just the airplane. So just the airplane there. And again, what we need to do is we need to think, well, what should we use for this? You know, we shouldn't be using that bearing as our angles. So if that was 340, that left us 20 degrees shy of all the way around. And so from our perspective of the trig, we're going to work this way to get to that angle. And what we would want to do is say, all right, well, that's going to be 90 plus 20, so that's going to be 110 degrees. So this is for the plane. So we take the magnitude, which is the speed, and we take 325 times the cosine of 110 degrees, and 325 times the sine of 110 degrees. But we realize that is not going to give us the whole picture. You know, that just totally erased there. So 325 cosine of 110 degrees and 325 sine of 110 degrees. But there is a wind, and that wind is going to affect that. So we're really looking for the resultant vector of the plane and the wind. And the wind would be a 40 for the magnitude, but remember that was 20 more degrees that we were looking at. The gap between, actually the angle between those two vectors was another 20 degrees. So that'll be 40 cosine of 130 degrees and 40 sine of 130 degrees. So the resultant vector will be what we get when we add those things together. So that's the component form for the velocity of the plane, 325 cosine of 110 plus the horizontal component of the other vector, and 325 sine of 110 plus the vertical component of the wind vector. And that will give us the component form that we need. So if you punch all of that mess in, you get negative 136.868 and 336.042 for the component form of that vector. And then part B says find the actual ground speed and the direction of the plane. So what we would have to do for the speed, remember in word problems the speed is magnitude, so we need the magnitude, the square root of negative 136.868 squared plus 336.042 squared. So that speed, otherwise known as magnitude with our vectors, is 362.846 miles per hour. And now we can work backwards here to figure out what that angle would be by saying, hey, here's our x component. And we got that by taking the magnitude of the vector times the cosine of some angle. So if we take negative 136.868 and divide it by 362.846, that equals the cosine of that angle. So we're going to need to take the inverse cosine of that to give us that theta angle. And the angle ends up being 112.161 degrees. But that's back in the trig, you know, and the people that are flying the plane, the pilots, they want bearing. So you have to change that 112.161 back into bearing. So you're going to have to take, well, you could basically just take 360 and subtract our 112.16, but then you have that original 90 degrees. So let me give you a picture here of where our 112 is at. So our 112 is over here. And what we want to know for bearing is from due north, how do you get to here? So what we would probably want to do is say, all right, that red one, if I just subtract from 180, I'll know this little angle theta right here. So if I take my little 180 minus 112.161, that's this little angle theta, so 67.839. So for the bearing, what I have to do is say, well, I need to go all the way over here and then up this little chunk of 67.839. Well, all the way over here is 270 degrees plus what we just had, and that is 337.839 degrees. So a bearing of 337.839 degrees. So here is the speed, which is the magnitude, and there is the bearing. And now we've answered all of that one. Next up, shooting a basketball. All right, so shooting a basketball. We have a basketball that's shot at a 70-degree angle with the horizontal direction. Fabulous. No bearing. That's 70 degrees. And it has an initial speed, an initial magnitude of 10 meters per second. So A says, let's just find the component form of that initial velocity. So that's going to be the magnitude times the cosine of the angle. Again, no bearing this time, so we can just go ahead and use what we have. And 10 times the sine of 70 degrees. And that is 3.420, 9.397. So what did we really find here? Well, what we really found is in B. It says give an interpretation of that horizontal and vertical component of the velocity. So the horizontal component what is that? Well, the horizontal component is the speed of the basketball. You're taking a shot, and that's how fast the ball is going. But the vertical component, you can't just get away with saying that's, going to be the speed of the basketball, because it's not. The vertical component is about, well, it is velocity, not just speed, because we're talking about having this go up and down. So the vertical component is the vertical velocity with the effects of gravity. On the basketball. That up and down piece is determined by gravity, the effect of gravity, along with, of course, the force that you are pushing that basketball with, but that has more acting on it than just the speed for the vertical component. Number 48, combining forces. Juana and Diego Gonzalez, ages 6 and 4, respectively, own a strong and stubborn puppy. You can see that in the picture, named Corporal. It is so hard to take Corporal for a walk that they devise a scheme to use 2 leashes. If Juana and Diego pull with the forces of 23 pounds and 27 pounds at the angle shown in the figure, how hard is Corporal pulling if the puppy holds the children at a standstill? So he just stops them right there. So let's see. Juana would be 23 cosine of 18 degrees and 23 sine of 18 degrees for the vector that would be formed by what she's doing. We've got our horizontal and our vertical components there. And then Diego, take note of the fact that Diego is going down from our horizontal. That's a negative 15. So 23 cosine of, oops, not 23, Diego is 27. 27 cosine of a negative 15 degrees. I better make my negative a little bit bigger, since that's probably where somebody messed up on this one. And then 27 sine of negative 15 degrees. So what do we get? Well, we punch that in, and we have 47.954 and 0.119. So we add those pieces. I mean, that's what we have to do. These two people, this plus this and this plus this, are getting us that component vector because they're both pulling at the same time. Now, we wanted to know how hard is the puppy pulling if he holds the children at a standstill. Well, this is how hard the kids are pulling. He's pulling equal but opposite. So here's your puppy. There's Corporal right there with those 2 negatives. And then what you have to do is find the magnitude, because it says how hard is that puppy pulling, and they are both pulling in terms of pounds. So we would have to use our little magnitude distance formula here, the square root of negative 47.954 squared plus negative 0.119 squared. And that comes out to 47.954 pounds. So this is all about the fact that his force is the opposite of whatever we get from their combined forces. So you add these 2 vectors together, just the horizontal components and the vertical components, and then we look at magnitude to see how hard the puppy's pulling. Number 49, in exercises 49 and 50, find the direction and magnitude of the resultant vector. All right, we've got a force of 50 pounds acting on an object at an angle of 45 degrees, no bearing. Love that. So there's a vector. A second force of 75 pounds acts on that same object. Negative 30 degrees. So this is very similar to the puppy problem. You know, we've got 50. That doesn't look like vector notation for components there. There we go. 50 cosine of 45 degrees and 50 sine of 45 degrees. And we need to add that to the other vector in component form. So 75 cosine of negative 30 degrees and 75 sine of negative 75, negative 30 degrees. So same thing as last time. Add your horizontal and vertical components separately and see what you get. And when you punch that in, we have 100.307, comma, negative 2.145. And they want magnitude and direction. So magnitude is again what we get when we do our little distance formula piece. So that'll be the square root of 100.307 squared plus negative 2.145 squared, and that comes out to 100.330 pounds. Now, if we want the direction, we have to use that component form of our vector that said this 100.307 equals the magnitude, which we just found, times the cosine of theta. And the good news is with this one that we were in first and fourth quadrants. So we should be pretty safe. We don't have to do a lot of thinking about all of the trig and which quadrants we're in. So 100.307 divided by 100.330 and inverse cosine. So we have 1.227 degrees. So the question comes up, why does the answer need a negative? Well, I want you to take a look at what we said. We said the component form of this vector was going to be 100.307 negative 2.145. What that tells us is we're below that x-axis. So the force of the resultant vector is here somewhere because it had a negative coordinate for the vertical coordinate. And that means this has to be a negative 1.227 because it has to be pulling it down.